Okay. All right. So this morning I thought I would go over the requirements of the logical program. Sort of what are the pieces that make this research program coherent? Um, so the basic pieces are that we want to be able to uh, take in as input the operational semantics of a model of computation and generate a logic um, for that system, so that we get formulae that correspond to each of the different pieces of the operational semantics. So together with the semantics associated with a means of collecting the results. So that last bit deserves a little bit of explanation. Essentially, we are going to be building a logic that satisfies two considerations. One is Curry-Howard. Propositions are types, and programs are proofs, right? So that's one piece of it. And the other is realizability. So those are all the pieces that are in play. And realizability says that the semantics of every formula is going to be the collection of witnesses of the formula. So in this case, it'll be all the instances of computation from the operational semantics that's given that bear witness to the formula. So that means that all these instances have to be collected in some way. So typically we collect in a lot of logical semantics, we collect things in sets. But the idea is that we might be able to collect them in things that are not just sets. Examples would be multi-sets, sometimes known as bags. And other examples might be distributions. So multi-sets are data structures where things can occur, the same thing can occur more than once. Right? So you might have a multi-set where you have 3 A's and 2 B's and 1 C. And that gives rise to an idea of distributions. So you might think about a probability distribution as another way of collecting things. And that would then allow our formulae to describe notions of fuzziness. So this idea, this set of desiderata, allows us to describe all of the dominant forms of logic that have been proposed over the last couple hundred years. So let me just grab an Emacs and okay, so I've got a little buffer and I will do a screen share.
when you say instances, on which part of the semantics you mean?
So when I say instances of computation, I mean terms.
Oh, okay. Terms on the value level, expressions or terms.
Yeah, exactly. So,
Okay, okay.
all right. So what we're saying is the input to the algorithm is one, an operational semantics, and two, a notion of collection. So operational semantics, uh, this is typically going to include a grammar for generating all the terms in the language / notion of computation. And it's going to include a structural equivalence or erasing syntactic differences. Don't make a difference. So for example, P par Q is the same as Q par P, right? Parallel composition doesn't care about the order that you write down the P and the Q because they're running at the same time. And C, a set of rewrite rules. For the evolution of computation. And then a notion of collection. Examples include set, multi-set, probability distribution.
Okay, can we use a graph here, or graph is the similar as list?
So I had hoped that we could use other things, such as list, graph, and other things. If we want this to work with distributive laws, then the no-go theorems for distributive laws eliminate that possibility. However, Christian has a slightly different approach for generating the structural formulae. So he's taking sheaves over a theory, over a second order algebraic theory. But he's using a topos as his sort of notion of collection, which is incredibly set-like. So we get toposes. So it also seems to be somewhat restricted to set-like ideas. I think we can actually recover the ladle notion from the sheaf notion, but that's some heavy lifting category theory that I'm not going to go into here. But the basic idea is that how do I say it? The key example that we want to use for all of this is models of linear logic. So sets of sequences. So sets of lists is the defining example. So if I can build a star autonomous category, well, if I can build a category that is a model of linear logic in a faithful manner, and use that as the base for my sheaves, then or and use that as the data in my sheaves, then um, then it might do the job um, better than so far it seems to do the job better than the distributive law, but it still seems to be committed to the set like notion of collection. Um, so in our but hopefully that explains the idea.
Yeah,
Um,
yeah, yeah, thanks.
cool. All right. So then what we want is to output a logic um, with uh, uh, the term operations lifted to formulae. Um, uh, so let's do it this way. One.
When you say lifted, do you mean like extended with additional terms, or
No, all of the term operations are also operations on formulae. So they started off
okay,
like as term constructors, and they become formulae constructors.
I see.
And then the collection operations are lifted to formulae. And that's because the meaning of the formulae, so satisfying realizability, meaning that the semantics of a formula is the collection of terms witnessing. And for Curry Howard. Let's do it this way. Meaning formulae types and proofs are programs. So that latter point implies that there is a proof theory. So I'll just put that as 4, but 4 is related to 3. Uh, um, so this is a logic with a proof theory / term assignment algorithm. So that's that's the aim. That's what we're trying to do. And you'll see that obviously if you do that, then you've got a type system, right? That's what the Curry-Howard does. And you've got a model checker. That's what realizability is doing. And you have a type checker. That's what the term assignment algorithm is doing. And you have spatial types. That's what this stuff is doing. You'll also, sorry, I need one more, which is, this is 3, this is 4, and this is 5. Modal operations. corresponding to the rewrite rules. Okay, that's it. That's the complete specification. So since we want to be able to include Christian's notion within this general framework, instead of calling it ladle, where we're restricting ourselves to the distributive law, we'll call this operational semantics in logical form. And this is a nod, you know, this is a gives a nod to Abramsky's domain theory in logical form. So that's what it is we're doing. If you don't have, and it's perfectly fine to not have any rewrite rules, right? In other words, it's okay if this collection is empty. So an example of the kind of thing that we could input would be a monoid, right? So here's the grammar for a monoid. So I've got some identity. I've got some generators, G1 through GN. Let me do it this way so they're not confusing. And I've got the multiplication. So that will generate, for some set of generators, G1 through GN, that will generate all monoid expressions. And then we have to add some equations. So these are the structural equations. So in particular, M times E is going to be equal to M, which is equal to E times M. And we also have the M1 times M2 times M3 is going to be equal to M1 times M2 times M3. So those are our structural equivalents, and then the collection of rewrite rules are empty. And now if we take our notion of collection to be set, all right, so the notion of collection is set, then we can now specify the terms in the logic together with the semantics all at once. So true is a term in the logic, and its meaning is L of M, right? So L of M is all the terms generated by that grammar. Is that clear?
Yes.
All right, cool. And then the meaning of not phi. Phi is a formula. True is an instance of phi, and phi is a general formula that we're now giving the recursive spec for, is going to be the meaning of phi. Take away in set theoretic terms, so remove, sorry. L of M. Come on, fingers. Take away the meaning of phi. So it's the complement. And then.
And this is the lifted logical operator, right?
For the collections.
Mm-hmm.
So, okay. Yeah, I'll talk to the pieces in just 1 second. And then the meaning of phi and the meaning of C is the meaning of phi.
Union. Wait, see.
Intersection.
Oh, oh yeah, yeah.
The meaning of C. Okay, so this are the collection formulae semantics, right? Doesn't mention anything about terms. This is just normal logic, right? And that comes from the fact that set is a model of normal logic, ordinary Boolean logic. Right, now we get the structural formulae. Okay, so the meaning of E as a formula, so I'll write it as caps so we can, but is going to be equal to all the terms in L of M such that T is equal to little e, right? So since that is true, right, then E star E is also in there, and E star E star E is also in there, right? Right, so this is actually an infinite set. Does that make sense?
Yeah, so this is all, for example, if this is a unit in Scala, we can write all of the unit expressions that can be different, but they're the same.
Yeah, that's right, that evaluate to them, yeah. Okay, then the same for each capital G, capital GI is going to be such that these things are equal to GI. Right, so remember we have G1 through Gn. So in particular, this will include GI, but it'll also include E star GI. And if there are any other equations, right? So if, like in modular arithmetic, you have that. If in so 2 plus 7 mod 4 is 5, right? So if you have any additional equations, then this will pick out those expressions as well. And now the more interesting one, let me grab it from here. And this is a lot like par. But see, we're taking the star from up here and we're lifting it to here, okay? And it's not going to be that, it's going to be, oops. M1 star M2 with M1 slash N and M2 slash N. So now what that does is it picks out all the terms that can be decomposed into a multiplication. So that's the structural formulae. And then if we, does that make sense? So everyone understand that last formula.
Yeah, yeah.
Okay, so this is an example I've been giving for years. So this is an example. And the point of this example is that even with this little example, we're starting to see things that we wouldn't see normally, right? So this is the usual logical stuff, and this is new logical stuff. And with this new logical stuff, we can write down a single line formula for primality. And then just because, for example, the row calculus includes a monoid, so we could take our monoid to be row terms under parallel composition with 0 as the identity. So then we would get these formulae. So we're ignoring rows rewrite rules for now. Then we would get this, but it would also give us a notion of single-threadedness. So primality gives us single-threadedness. So people are wondering what the thing for primality is. So prime is going to be, well, it's not allowed to be the identity, so it can't be E. And it's not allowed to be the parallel or the star of two things which are not the identity. So that's prime. That's the definition of prime. So that's a new kind of formula. It's a one-line formula, and it picks out all of the terms which are prime, which happens in the case where we've set our monoid to be row calculus terms under parallel composition with 0 as the identity to be single-threadedness. So this one formula suddenly opens up this whole world of relationship between arithmetic and number theory and concurrency. So this one example is sufficient to generate interest in this research program, right? So the program is to find an algorithm that is going to generate this example, right? Which has all of these desiderata with the exception of the modal operators. But even here, things are quite interesting because, for example, if instead of picking out monoids, we picked Clifford algebras, then our formulae would be all about geometry instead of about monoids, which are certain kinds of actions. So this is a very, very interesting and important idea, and it has a reasonably well-established predecessor, which is Abramsky's domain theory in logical form, where he does the same thing, but instead of for operational semantics, he does it for denotational semantics. We're arguing that the denotational semantics is the more natural way of thinking about computation, and is certainly much more widely practiced than denotational semantics. When we're talking about the modal operator, hang on, let me I'm just looking for that's weird. I thought I had it. I guess I don't. Okay, so let me grab it from Emacs. All right, so here we go. So the basic idea when we're moving this to include rewrite systems, and that's what this is all about, right? So we're going to assume that there's at least one term constructor that is essentially binary, morally binary. So it's going to take at least two things here and produce a term. So like par as an example. Or application. So par in the row calculus, application in the lambda calculus. Takes two things. So par takes two processes. Lambda takes two terms, produces a term, right? The lambda produces the application of one term to another. Par produces the parallel composition. So we have to have at least that. And once you have that, then you can now define a notion of arrow, because you can take a term and you can knock a hole in it. So that'll give us a notion of context, and that's going to be important. And then you get, if K is, so K can be commutative, like par is, or it can not be commutative, like application is. And you'll get two arrows, depending on whether you knock the hole in the left or the right. And so this is going to be all the K formed terms where you've knocked a hole in it, such that whenever the term is filled with, when this hole is filled with something from tau, when you take that rewrite step from K of t to u prime over to v, then you get something that's in tau prime. So the arrow from tau to tau prime is all the terms formed with K that have a hole in them, such that if you fill the hole with something that's in tau, that's what this at sign says, is fill the hole, and we're insisting that we're filling the hole with something from tau. Then in a single step, if it rewrites at all, it's going to rewrite to something that's in tau prime. So that's the formula that gives you the notion of modality. So in particular, we can recover the Hennessy-Milner notion of modality, and we can recover the lambda arrow type. So, the basic functional type you find in Scala can be recovered from this definition, as well as the Hennessy-Milner modal type can be recovered from this definition. And that then goes back to what we were saying about the modal operations corresponding to the rewrite rules. So that's the general shape of what it is we are trying to do. What I've tried to do is to motivate this shape so that people understand a little bit more about what constitutes a solution to the problem specification, and why this problem specification is important. So let me just stop there and see if there are any questions. Was this helpful to people? I know some people are just coming into this, and other people like Tomasov have been exposed to these ideas for a while.
Yes, but every time it's helpful for me to understand even more. So yes.
Good.
Agreed. I'm getting more insight as well.
Cool. Is there any specifics in terms of what was new understanding for you?
Oh, well, actually, my new understanding is with a better understanding of what K is and how it's two terms and the relationship to the whole. So I've been hearing a lot about that over the past few weeks, but just having it explained in a different way just kind of shed a light to illuminate what exactly that is.
Oh, that's good. That's very good. Thank you. For you, Tomislav?
For me, I was just thinking how you were explaining the structural part, and with rewrite rules. Now I'm understanding why you are talking about this labeling, because this is somehow similar to structural equivalence, but this is like more complicated because rewrite rules are not only structural, but with modal logic we are somehow doing the same thing, right? We are
Yes, that's correct. We're with the modalities. It's related. The thing is that the structural stuff is, you can think of it as bidirectional rewrites. So because they're equalities, right? So here's an example of an equality, right? Right. You can go either direction. So that means you can think of it as two arrows, right? One going from one form to the other. So that's, whereas rewrites, what that means is that you don't forget any information. You don't lose any information. You can always undo what you did. But with lambda, with beta reduction, when you apply the substitution, you've lost where you came from, because lots and lots of different applications could result in the same term at the end. The same with com, right? There's lots and lots of parallel compositions that could result in the same term at the end of that step. So that means that you've forgotten information. And if you go look at the work of Bennett, who gave a resolution to the question of how computation is in compliance with the laws of thermodynamics, then you can understand why the rewrite rules need to forget information. So if you remember the Maxwell's demon problem, right? So the idea is that you've got some chamber full of molecules that are high energy. Well, they're of an energetic mix. So some are high energy and some are relatively low energy. And you divide it with a barrier. So you take the chamber that's now got this mix of molecules that are bouncing around, and you put a barrier right down the middle of it. And you have a little trap door that's controlled by a daemon. And the daemon checks to see if a molecule has a certain amount of energy, and it lets all the molecules of a certain amount of energy to one side, and and is essentially separating the room into a collection of high energy molecules and low energy molecules, which is now it's decreased the entropy in the mix of molecules. And so the question is, what prevents that? And in particular, if you replace the daemon with a computer, now you have you could build such a system, right? And so the question is, where's that entropy going in the computation? Because that's the only thing where the entropy, you're decreasing the entropy in the chamber, but you're so if you're going to observe the second law of thermodynamics, where entropy is always going to remain the same or increase, then the computation has to result in an overall net increase of entropy. And Bennett solved this problem showing that the computational device has to essentially reset itself, right? It can't grow infinitely in terms of memory or other resources. And it's the forgetful steps that actually increase the entropy in the computation. And so in general, if you're going to have Turing complete, so this is right up against quantum mechanics, right, which is all reversible. But in the classical world, if you're going to have a Turing complete classical computation, there has to be a forgetting. Otherwise, you would break the second law of thermodynamics. So that's why these rewrite rules have to have some form of forgetting. Otherwise, you wouldn't observe the second law of thermodynamics. They wouldn't be physically realizable, not classically. So that's a little bit of background on the way this stuff begins to make contact with the real world.
Is this related? You said that we need K as interaction in our language, and from T2 to T. Is this also like a source for that? Because we have 2 of something and we are reducing this to 1. So we need to forget something.
K is the model of interaction. K is telling you how things interact. Right? So it's what happens when the molecules bump into each other.
And this doesn't mean that we must lose something, or...
That's right. That's right. That's what I'm saying. So K is exactly interaction, right? And that's why, and this is the key step, right? So the important point, the important observation that Milner has when he thinks of the process calculi is he thinks about computation as interaction, which is in alignment with physics, right? Physics is all about interaction. Up to that point, nobody's thinking about computation as interaction, right? So if you look at finite state machines, they don't model the environment. Lambda and the pi calculus model the environment because you have a notion of computation as interaction between 2 things. Now, in general, interaction could be, between more things. Statistically, it becomes harder and harder for that to be the case, right? It's harder and harder to have in things collide or interact in some way. But yes, K is divided into 2 because it's all about interaction. And then you get this ability to flip back and forth, right? Because even though K is divided into 2, there's nothing that says what is program and what is environment. So you get a duality where you say, okay, well, this part of K is program and that part of K is environment. And then you can flip it around and you can say, okay, that part of K is program and the other part is environment, right? So program and environment becomes a relative term. Does that make sense?
Yeah. So when we are deploying rolling to the network, the network can be like an environment, right? And our code is on one side.
That's right. That's right. That's one way to think about it. In general, for Turing complete languages, you're going to have a representation of the environment as program. And the extent, how do I say this? When you deploy your program to the network, its interaction with other things, if you want to have any sort of how do I say this? Good handle on that interaction. You need to be able to represent the actions of the environment as programs. Does that make sense?
Yes.
Right.
Yes.
That's why, for example, the Keebler-Elves strategy for concurrency is a bad idea. So, you know, writing programs in some sequential language and then, you know, trying to auto distribute and make it all work concurrently in this automatic fashion is a very bad idea, because you will suddenly get failure modes that are not represented in your language, right? So, so, you know, message duplication, message loss, all of those things, you know, are not represented in your language, and as a result, you can't present to the programmers the source of the errors, because they were magical and invisible. So that's why this program is much more sane. Yeah. So anyway, I thought it's important. Essentially, what we've done today is to introduce the you know, the sort of the nomenclature, the name of the research program. So we've taken it up a level from ladle to include this sheaf idea. So it's operational semantics and logical form. We've identified we have identified the algorithm that we're seeking in terms of constraints on the input and constraints on the output. And we've given an example of something that satisfies the algorithm. Although we didn't give a proof theory for it, but we could give that proof theory, and that's what we did. Examples of that are in the paper that I've been talking about. And then the other thing that we've done is, although we didn't talk about this morning, it turns out that when you do the proof theory, no, that's not quite the way I want to frame this. There are different notions of negation. And this is where the linear logic stuff becomes. So remember, I said we might want to include a different kind of collection up here. So notice that I've used set complement for my interpretation of negation. So that works in this example because we don't have any rewrite rules. If you look at Kairos' spatial behavioral formulae, spatial behavioral types, his negation also has no relationship to the rewrite rules. However, if you look at the session types, the notion of negation there is related to the rewrite rules. So essentially, that's what's going on when we're talking about this this notion of arrow here. If we put a notion of false, whatever that might be. So for example, it could be termination. If we put 0 there, or some notion of termination that we've introduced into the lambda calculus, a kind of, you know, a null term or a stopped program. If we put that in the right-hand type, then this becomes a kind of negation. And but it's a negation that's related to the rewrite. Right? So that negation is different from the notion of negation that we get when we use set complement. And that is the essential difference between session types and the Kairos types. So the framework also allows us, so the shape that we're giving here to things allows us to begin to explain the relationships of all the different logics. So we can explain the relationships of the modal logics to the functional types. We can explain the relationships of the session types to the Kairos types. A huge number of logical phenomena that have appeared to be different are in fact the same. So that's the other thing that's in the in the sort of research program, is that it becomes a unifying framework in which to understand all of these different logics. In general, there have been, sort of classical logic, intuitionistic logic, substructural logics, where you get rid of, say, weakening or contraction, which is related to linear logic, which is related, and then there's the modal logics. So all of these different kinds of logics would like to understand their relationships and know how they fit with respect to each other in terms of what they pick out in terms of computation, the kinds of properties they pick out in terms of computation. And this program identifies a very, very large number of those relationships. So that's a side benefit that we haven't identified here, but turns out to be quite useful and quite powerful. So that's the other reason for this particular research program. And then there's the fact that it saves the industry a lot of money. Because when you generate the logics in this way, they're automatically sound and complete. So Scala's type system, for example, was ultimately proven to be unsound, which is why they had to redo the Scala semantics and types. JavaScript, as I've said many times before, is broken because it doesn't have a type system. And the industry has spent hundreds of millions of dollars rectifying that situation, and it's still not rectified because you have 3 different kinds of typed JavaScript, because all the type systems are done by hand instead of algorithmically. And then, of course, as we pointed out, the formulae that we get from these logics generated in this way, have more power than than the kind of formulae that we got from, say, ordinary Boolean logic. So you can say things that you couldn't say before, and because you can say things like that, you get you get a much more insight into what the program does and how the program is structured. So this formula tells us how the program might be structured. The program is not allowed to have threads. So that's an example. And then once you see that, then you realize that you can use these formulae in the same way that relational algebra is used to generate a query language. You can use these formulae as query for repositories of programs or other kinds of structures specified in this way. And since we specify almost all data in this way, and code is a kind of data that we would like to manage, this becomes useful in that way. So yeah, I just wanted to make sure that we had a, you know, we refreshed what it is that we were going after when we go after these this research program and why it's relevant, and because we're about to start seeing the academic community take this up, and so it's going to be taken in a lot of different directions all at once. Once it starts to take off, a lot of people will take it in lots of different directions, and it's kind of important to understand what the original impetus and motivations were. Any final questions or thoughts?
I was wondering, you mentioned before part preserving under negation, and this is what you are referring to rewrites under negation, right?
I didn't say par preserving under negation. The negation has to be par preservation for translations is important, right? It's one of the ways. For example, Contusia Palamadisi is able to show that there is no par preserving translation of mixed mode IO. So a version of the pi calculus that has mixed summation, right? So you can sum over output and input. You can't have a par preserving translation of a calculus like that down to the asynchronous calculus without, you know, with no mixed mode summation. So par preservation is an important expressiveness feature. With respect to negation, this negation is not going to respect evolution. So the negation we have on screen won't respect evolution. So in particular, you won't have that the things that are in phi, that if phi is a modal formulae, will be that the complement will respect the evolution, right? So you might have things that through evolution are still in the complement, right? So that's a so basically this kind of negation has no information about evolution, whereas this kind of negation, where you put something here as your what's called a dualizing object, right? Whether it's 0 or something else that you pick as your dualizer, this will have information about evolution because it's built into the definition.
I see.
Yeah. Does that answer your question?
Yes, thanks.
Cool. All right, it's 8 o'clock, time for stand up. Thank you very much to everyone.
Thank you.
Thank you.